So hello everybody, and welcome back to another RUS webinar. My name is Miguel Castro, and today I'm here back with another topic in this series of RUS webinars. So today we are using Sentinel-3 data to do land monitoring, as you can see in the title of this webinar. And before starting, let me tell you the objectives of this session. So you will learn two main things. First, how to do land monitoring analysis with Sentinel-3 data. And second, what is the RUS service and how it can help you in your projects with Sentinel data. So therefore, for this exercise, we will combine both RUS and Sentinel-3 for our land monitoring analysis. So just before starting, be aware that this webinar is being recorded and that you will be able to repeat the exercise by yourself. But don't worry about that. I will explain you how to do it later in the session. So let's move and let's get started by having a look to the outline of this webinar. So we will start by checking our study area for today. We will see some details that are needed to understand what we are going to do and also to interpret the final result. We will then cover the theory behind the use of satellite Earth observation for this type of applications and how the data from space can be helpful for land monitoring. We will then describe what is the RUS service and what are the capabilities, and then we will use this service to perform the exercise of today. And at the very end, we will have some time for Q&A session. So since we are quite a lot of people here today, I would ask you please to send your questions as soon as possible. There is a dedicated option in the GoToWebinar, so please use it and send the questions as soon as you have them so that we are sure that we can reply to as many questions as possible. So the complete duration for this webinar is going to be more or less 1 hour 30 minutes, depending on this Q&A. So let's get started, and as you can see, let's go to our study area. So this time we are traveling to Cyprus, the third largest and third most populated island in the Mediterranean. We could say a lot of things about this country, but we want to focus on its climate and vegetation to understand how they affect land surface dynamics. So if we talk about the geography of the island, if we talk about topography, the physical relief of the island is dominated by two main mountainous areas, the Troodos Mountains in the west and the Kyrenia Range in the north, and a central plain known as Mesauria, where the largest river of the island is located. So in this image, you can see those mountainous areas, mainly this one here, and then the one in the north. And in the middle, we have this plain. About its climate, Cyprus has a Mediterranean and semi-arid climate with very mild winters and warm to hot summers. And as in many other countries of this region, rain occurs mainly in winter, with summers being generally dry, or very dry actually. So this is going to be today the area we will use for the land monitoring exercise. So let's move now to the remote sensing background. Well, reliable information on land dynamics is required to improve, for example, agricultural management, to map our changing land, and to face food security challenges, but of course also to monitor the effects of climate change. For that, different methods can be used to gather this information, but satellite Earth observation techniques offer a suitable approach based on the coverage and type of data that are provided. The imagery data from the Sentinel satellites enables a new approach for land monitoring. The combination of their temporal, spatial, and spectral resolutions, together with relevant analysis, can lead to improvements of the decision-making process. And this is the context of how satellite data is used, in this case for land monitoring. So for this exercise, we will be using multispectral data provided by the Ocean and Land Core instrument, better known as OLCI, of the Sentinel-3A satellite. In case this is the first time you heard about them, the Sentinel satellites are included in the space component of the Copernicus program of the European Commission and the European Space Agency. The Sentinel-3 satellite is, let's say, the most complex of the Sentinel missions, since we have a multi-instrument platform carrying 4 sensors that work in synergy. Although we are using for this exercise only one, let me introduce you very briefly the 4 of them so that you have a good overview of the satellite. So first of all, we have what is known as the Sea and Land Surface Temperature Radiometer, which is also known as SLSTR. It measures the global sea and land surface temperature every day to an accuracy of better than 0.3 Kelvin. So that's pretty accurate. So for example, in this image here, you can see actually the first image that was released by this sensor, and it's over the coast of Namibia. So you can see different colors for different temperature ranges, both over the land and also over the ocean. So as you can imagine, there are a lot of applications that can benefit from this data. We then have the Sentinel-3 topography package, which is formed by the synthetic aperture radar altimetry instrument, better known as SRAL, and the dual-channel microwave radiometer. So together, they measured the height of the sea surface waves and surface wind spins over the ocean. They provide also accurate topography measurements over sea ice, ice sheets, rivers, and lakes. And as an example in this image, we can see the height of Antarctica's ice sheet derived from the data of the topography package of Sentinel-3. And then we arrive to the ocean and land color instrument, the OCHI instrument, which is actually an improved continuity of the NVSat METIS instrument. In case you have been working with remote sensing data earlier, you maybe know this sensor. So we are using the data from this sensor today, and because of that, let me give you some extra details about this sensor. So we can see the OCHI sensor as the big brother of the multispectral imaging instrument of Sentinel-2, but of course with some differences. So first of all, we have a wider swath of 1,270 kilometers with 21 distinct bands in the 0.4 to 1.02 micrometers region of the spectrum. The revisit time is less than 2 days at the equator once the constellation of Sentinel-3 is completed. And the spatial resolution is 300 meters at full resolution and 1.2 kilometers at reduced resolution. So let me show you a comparison with Sentinel-2 so that you have an example of what we are talking about. So here we have a Sentinel-2 image over Cyprus. It's 10 meters pixel size. But if we have a look to the same area in Sentinel-3, well, this is how it looks like. So yeah, nothing very clear. We can see more or less the urban area in the middle, but nothing else. So you can think that in that way, Sentinel-3 is not very useful if we compare to Sentinel-2, but of course this is because the applications are not the same. For example, if we zoom out a little bit, we will see the coverage of a Sentinel-3 image, and if we now compare this to Sentinel-2, well, it's very small. So as you can see, depending on what you want to do, you will find Sentinel-3 much better than Sentinel-2. Of course, if you want to zoom in a lot and do something very precise, Sentinel-3 is not your sensor, but then you have Sentinel-2 and the other way around. So, as you may know, there is only one of the two Sentinel-3 satellites up in this space. So, according to the last news, Sentinel-3B is coming next 25 of April. So, stay tuned for that now that there is a hype for rocket launches. You can also see the Sentinel-3 launch next month. So, let me introduce you the different data products that are delivered by the OCHI sensor. Because this is very important, because once you want to download the data, you have to understand the different products that are available. So we have the OCHI sensor doing its job and delivering data back to Earth. So first we divide the data, in two levels, 1B and level 2. So in level 1B, we can find the top of the atmosphere radiometrically corrected measurements, which are also calibrated and spectrally characterized. The pixels are orthogeolocated, so we have latitude and longitude coordinates, and provide values in radians units. So in level B, this is the output you get when the sensor is in what is known as Earth observation mode. There are other modes, but I will not go through them since I want to keep this explanation as simple as possible. So those top of the atmosphere radiances are delivered in two ways. Full resolution, that is, the pixel size has more or less 300 meters, and then reduced resolution, then the pixel size is 1.2 kilometers. Then we have the level 2 products, which consist of geophysical quantities derived from the processing of measurements data provided in the Level 1 products. Level 2 products, specifically for marine and land applications, are generated separately. And why? Well, because you do not want to derive the same geophysical parameters over land that over ocean. So that's why we split it. So for land applications, we can get the OLCI Global Vegetation Index, the Terrestrial Chlorophyll Index, and the Integrated Water Vapor. And again, those are available in full resolution and reduced resolution. For water applications, there is also a long list of geophysical parameters that you can get, but I will not go through them since it's quite long, and today we are focusing on land. Just remember, you can also get them in full resolution and reduced resolution. And finally, be aware that the products of Level 2 over land are managed by the European Space Agency, and the ones for water are managed by EUMETSAT. So depending on which one you want to get, you will have to go to the CODA website where the Level 2 for water are available, and if you want to work with land, you have to go to either the pre-operations hub of Sentinel-3, or once it's in operational mode, into the Open Hub as for Sentinel-2. So if you are interested in knowing more about CODA and Level 2, we had a previous webinar last month where we used OLCI data Level 2 water products, so you can check that, but I will explain you where to find this information later. So knowing Sentinel-3 and the different data products that are available, let's now move to the RUS service. So RUS stands for Research and User Support for Sentinel Core Products. Sorry, yes, there you go. It is an initiative founded by the European Commission and managed by the European Space Agency with the objective to promote the uptake of Copernicus Sentinel data and support research and development activities. The service provides a free and open scalable platform in a powerful computing environment, hosting a suite of open source toolboxes pre-installed on virtual machines, which allow you to handle and process the data derived from Sentinel satellites. So what does that mean? Well, with a large amount of data we have from the Sentinel satellites, and with more Sentinel coming up in the next months and years, the challenge is no longer data availability, but rather storage and processing capacity. So to solve that, RUS offers virtual machines so that you can have the appropriate computing environment to handle the data. And in addition to that, RUS also provides a specialized user help desk to support your remote sensing activities. So that means that if you are working with Sentinel data and you are a RUS user, you can send us your doubts about how to use Sentinel data, and a team of remote sensing experts will come back to you with solutions so that you can keep moving with your projects. And in addition to all that, we also have a dedicated training program, such as the webinar we are doing today, and also face-to-face events. So all the information of the RUS service can be found in those two main websites. So let me go very quickly through them so that you can get the complete picture of RUS. And there we go. So this is the first one, the rustraining.eu, and here you can find all the information that is related to the training activities of the RUS service. So something that I want to highlight in this website is the training tab here. If we click, we can either access the upcoming webinars or the past ones. If we go to the past ones, actually, we see the complete list of webinars that we have organized in the past. And for example, if you are interested, as I said before, in OLCI data for water, you can go to the webinar that took place last month, and by clicking here, you can access the recorded video and also the Q&A session document with some of the most important questions that we replied during that session, and also some instructions to repeat the exercise. But don't worry, I will explain you later how to do specifically this, how to repeat the exercise. You can also find in this RUS training portal the e-learning section. So here we have different material that can help you to improve your knowledge about remote sensing concepts. So we have started so far with a series of SAR lectures. So here you can find different courses to improve your knowledge about radar and SAR Earth observation. So we go now to the second website, which is rus-copernicus.eu. Here you can find all the information about the service. So something important to know is that it is here where you can register for the service and become a RUS user. And as I said before, we offer virtual machines that come with pre-installed software. So if we go to the RUS offer and more in detail to computing environment, you can actually see the list of software that is already installed in the virtual machines and which is ready to use. You can also access the different types of virtual machines that we provide. So depending on your project and depending on the requirements you need, you will receive a different virtual machine in terms of processing and storage capacity. So here you can see the different specifications of the RUS free virtual machines. So knowing that, let's see how you can become a RUS user. So the first thing you have to do is to register for that. So we have here this registration tab in the upper right corner. So we click here and we click on register. So it's very easy. We just have to fill in the information and then the account will be activated. This process of activating the account can take 1-2 days, so expect that it will not be completely automatic. So once you have your account, you can log in on the website. So we go again back to the login tab. Now we click login, and if I access my account, I will show you how it looks like. So once you are in RUS, into RUS, you have this dedicated menu here. And the important part is your dashboard. So it is here where you will be able to access the virtual machine. So let's have a look. So now what you can see here is actually the 2 virtual machines that I have assigned, and this is because I have already done the application for those virtual machines. But if it's the first time you are joining RUS, you will see that there is no table here displayed to you. So what you have to do is actually apply for that virtual machine. And for that, we click on request a new user service. So we'll click here. It's now when you can tell us which is your project, what are you going to do, so that we can understand your needs. So let me show you the procedure so that you get familiar with it. So first thing we have to do is to specify the years of experience we have, if we have already handled Copernicus data, and if we have already processed this data. And now we have this box here where the application is asking us if we want to repeat a webinar. For example, let's imagine you want to repeat the webinar from last month. So here you have to specify a training code. This training code will be provided to you at the end of this webinar if you want to repeat this webinar. If you want to repeat other webinars, you will find them in the RUS training portal. So for example, let's imagine we want to repeat the webinar which code was LAND01. So you can very easily put this here and then specify if you want to use the virtual machine only to repeat the webinar, or if you want also to perform additional analysis in your own projects. So for example this. And now we click next. So in the next step we have to specify some extra data, for example the thematic area, also the kind of operation we are going to perform, and if we want the RUS service to download the data for us or not. So this is actually a very nice feature of RUS. Imagine you are working with a large data set of Sentinel imagery, let's say 80 Sentinel-3 images. And so you need to download this data to the virtual machine. So you can either do it by yourself or you can ask the RUS service to do it for you. So once you receive your virtual machine, all the imagery will be there, ready to use, and you can skip that part and start with the analysis you want to do. So in my case, I want to do self-downloading, and now here I can put some extra information about the project. Think that the more information you give to us, the better for us to understand your needs. And of course, we can also give a name to the project. So then we click next, and then we are in the last step. We need to specify the type of data we want. So today, for example, we are using Sentinel-3 data. We will be using the Olchi sensor, as I told you before. And we can also specify the region. So in this case, it's Cyprus. We can also specify the region of interest by uploading a shapefile containing the polygon of our study area. So this is actually very convenient as well. And then we can specify if we want to do a multi-temporal analysis or not. So for example, if we say yes, well, we just need to specify the sensing period. If we say no, that's all. And at the end, some extra information again about the project, something that you need to clarify about the data, etc. So once you are done with the application, you can just check all the information you have provided. And once you do that and you agree with the terms and conditions of the service, you can click here and then submit the request. So once you submit the request, it will be checked by our front desk, and they will come back to you in a few days, let's say 2 to 3 days, with a response to your application. So they will check your needs, they will think about which type of virtual machine you need, and they will send you all the information within 2 to 3 days. So I'm not going to submit this request because I have already 2 virtual machines, so I'm going back to the dashboard and show you the next step. So once you receive the confirmation to your virtual machine, this is what will happen. You will see this table here in your profile, and through this table you can interact with the virtual machine. So the most important thing that you can do here is it's obviously access the virtual machine. So you can click here in access my virtual machine and you will go to the virtual machine. You can also, for example, get support. I told you RUS also offers support for Earth observation doubts. So if you don't know how to do some specific things with Sentinel data, you can click here and write your doubt, and then a team of remote sensing experts will be there to help you in your process. So that's all for the introduction to RUS. Now let's start our exercise for today, and for that let's go to the RUS virtual machine. So for that, you can click here. I already have my account, sorry, my virtual machine open here. So before starting, because now we are starting the exercise, just remember, if you have doubts during the exercise, don't wait until the end. Just send it to us as soon as you have the doubt. So here we are in the RUS virtual machine. Well, this is an environment that is based on Linux. So if you are familiar with Linux already, you will not have any problem to adapt to it. But anyways, it's very easy. This is like a regular computer. We have our dedicated internet browser here, which in this case it's Mozilla. We also have some icons that some of the software that's already pre-installed on the virtual machine. So you can see here, for example, Snap, R, etc. And you also have a dedicated file manager to store all your data. So something important to tell about the virtual machine, we get a lot of questions about that, is how to interact with your local computer. So let's imagine you have done an analysis in Snap with Sentinel-3 data and you arrive to your final output. And you want to download this output to your computer. So you do that by pressing the keys Ctrl-Alt-Shift, and then this side menu appears. So now here in device, you can click here and you will access all the system of the virtual machine. And you can navigate to a specific path where you have, for example, your output, and you can download it. How to download it? It's very easy. You just need to double click on the file you want to download, and then a regular download process will start. If you want to upload files to the virtual machine, it's again the same. You go to the path where you want to save the data and you click in upload file, and then just select the file, and that's all. So let's start the exercise now, and let me give you some extra details about what we are going to do today. So in this exercise, we will do, as stated in the title, land monitoring. For that, we will use the cloud-free Sentinel-3 images available for 3 consecutive months, May, June, and July 2017. We will process the data, and we will derive a mean NDVI image for each month. And then we will analyze the temporal evolution of this parameter to get an idea of how the land surface dynamics are and how it evolves over time. So for that, the first thing we have to do is to download the data. So today we are using, if you remember the diagram that I showed before, level 1 products. So level 1 products can be downloaded actually from ESA or from EUMETSAT. So today I'm using the ESA site, and let me show you how to do it. So we open the internet browser, and we need to go to the Sentinel-3 pre-operations hub. So Sentinel-3 is still in pre-operations. Once everything is set for operational mode, the access point through ESA will be the open hub. But so far we have the Sentinel-3 pre-operation. So we click here, and we access a very similar the same interface as the operational hub. So the first thing to do is to log in the system, or if you don't have the account, to create one. So let me just log in with my credentials. There we go. So what to do now? How to download the data? Well, the first thing is to navigate to our study area. So for that, we use the pan option and we go to Cypress. There we go. And next, we need to define our study area. And for that, we use the box or the polygon option. So today I'm using the box like this. So this is going to be our study area, the complete island. And then we need to specify the data we want. So for that, we open the side menu here. And the first thing is to define the sensing period. So for example, I want to not for example, but today we are using a sensing period from the 1st of May until the end of July of the same year. Okay, once we have the sensing period, we specify the mission, in this case only Sentinel-3, and then we can put some parameters to access the products we want. Remember the diagram I was showing before, so it's here where you can trigger the database so that you get the appropriate result. So we want to use ALCHI data, we want to use level 1, and we want to have it in full resolution. So all those acronyms that you see here are the ones that I was showing before. So here we have all for ALCHI, 1 for level 1, and then this is FR full resolution or reduced resolution. Here we have the level 2 products. So ALCHI level 2 LAND full resolution or LAND reduced resolution. The other things you see here are the products from the other sensors on board Sentinel-3. So forget about them. Today we are only using ALCHI level 1 full resolution. Okay, and once we have this, we can just press the search icon and get the results of the query. There it goes. So you can see actually we have a lot of products available. So what to do next? How to download the data? Well, the first thing I would say you have to do is to check the image, check if it's the one you want to download. And for that, you can access the details of the image in this eye icon here. So if we press here, you can see, for example, some metadata of the image, of the product, instrument, etc., some parameters that might be interesting for you. And then we have here this quick look image. So this is very convenient because if you are looking for cloud-free images, you can visually see if your area is covered or not by clouds in a, let's say, in an easy and fast way. So what we are going for this exercise today is to download all the cloud-free images for May, June, and July 2017. So once you have identified this image, you can just click here in the arrow and the process will start. So you can see that the image is being downloaded to the virtual machine. And remember, we are working in the virtual machine. We are not crashing our computer with tons of data. So since we are working actually with a lot of images, let me just show you the dates we are using today. So we will be downloading 7 images in May. So here you can see the dates, more or less all over the month. We are also downloading 8 images for June. And then we are we are also downloading cloud-free images for July. So in total, we have 22 Sentinel-3 ALCHI level 1 full resolution products. That's the complete data set we are using. As you can imagine, I'm not downloading the data right now. I've done that already, so we can start our analysis straightforward. So, so the next thing we have to do is to start our analysis in the software we want to use to process the data. And for that, we open Snap. So, yeah, okay, so let's open Snap. There it goes. I had it open already. So if it's the first time you are seeing Snap, let me give you a very brief introduction to the software. It's very easy. We have here the Product Explorer where we have the products that are open in Snap and that we are working with. We also have some quick menus here in the lower left corner that help us to work with the data. For example, the world view to see the location, the footprint of the images we are using. We have this main gray area here where the display of the images will take place once we open a band. And we also have here the tools we need to analyze the data in this main toolbar. They are also organized by menus, so for example, raster tools, optical tools, or radar tools, depending on the Sentinel sensor you are using. So let's get started and let's open our true color RGB composition. So I have the product already open in Snap here, but just to show you how to open a product in Snap, a Sentinel-3 product, well, you click here in the open product icon, you navigate to the path where you have stored your image, and once you have downloaded the Sentinel-3 image, and once you have unzipped the product that you receive from the server, you can open the folder and select the XML file. This is the file you want to select to open the Sentinel-3 image in Snap. So I've done that already, and here is my image. Now we can see actually a lot of information only in the product name. So we see, for example, this is a Sentinel-3 image from the Olchi instrument, level 1, full resolution, and the sensing time. So just by the name, you can already get a lot of information. But you can also expand the product and access much more. For example, metadata about the image, etc. The relevant folder here is the bands folder. It's here where you have the measurements, the bands, plus other products that are together. So for example, in the irradiance folder, we can access the 21 spectral bands of this sensor. So to visualize the data, we are going to open a true color RGB composition. And for that, we right-click on the product and we select Open RGB. Here we can define the profile for the red, green, blue channel. So I'm selecting a different band combination to show you the true color composition. So in this case, for Sentinel-3 is 864 for the red, green, blue channels. And we click OK. And now we have here the true color composition. There it goes. As you can see, it's very dark. And this is because the colors are stretched according to the maximum and minimum values of the histogram of the image. So how to change that? Well, we have here the color manipulation menu. And what we need to do is to move a little bit, well, we need to move the slider so that we stretch the colors in a different way and we improve the view. So I'm just moving it more or less like this. And if we do the same for all the channels, the red and the blue, you will see that we end up having actually a nice, well, it's too reddish, so we can just change this. There it goes. Well, you can tune this a little bit so that you get, let's say, what we are all used to see as a true color composition. So we can now zoom into our study area, which is Cypress, that we have, Cypress, and we can also move around the image by using the pan option here. So we can just use the hand to move around, as in many other GIS and remote sensing software. So now that we have this image, we can start our methodology. So remember, we have 22 Sentinel-3 images in total for the analysis of today. So I'm going to show you how to do the analysis only for one of the images. And then we will use what it's called batch processing to run the same analysis in the remaining images at the same time. So let's go through the procedure step by step. The first thing we need to do is to create a cloud mask. So the objective of the first step of this methodology will aim to remove cloudy pixels from the image. For that, we will use the IDPix processor that is available on Snap, which provides a pixel classification into properties such as clear or cloudy, land, water, snow, ice, etc. The products we have downloaded already contain a cloud mask, but it can be improved using this tool. And in addition to that, it allows us to convert the pixel values from radiance to reflectance at the same time. So remember, radiance is the variable directly measured by the remote sensing instruments. It is the amount of light seen by the instrument from a surface of an object. Reflectance, on the other hand, is the ratio or percentage of the amount of light leaving a target to the amount of light arriving to the target. So it has no units. So let's create our cloud mask and convert the pixel values from radiance to reflectance. For that, we go to Optical, Preprocessing, Masking, IDPix, Sentinel-3. You can see this processor is available for many of the satellites. But today we are working with Sentinel-3 Olchi, so let's select this option. So here we have the common Snap interface for the tools that are available in the software. We have first an input-output tab where we define the input of the tool, and then we have the output area where we define the path where we want to save the product, the output of this tool, and also the name that will be assigned to this output. So as you can see, the default name is the input name plus a suffix that represents the tool that has been used. So actually this is very convenient when you are combining a lot of steps, because in that way you can keep track of what you are doing. So we leave here everything as default, and then in the processing parameters we can specify which bands do we want in our product. Do we want to create the mask that IDPix produced together with radiance values in the pixels or in reflectance? So as I said, I'm selecting reflectances today. Remember, top of the atmosphere. So here we have the selection, and once this is done, we just need to press run. So I'm not pressing run because the process takes some minutes and I want to save time for this webinar, so I will show you directly the output, which I have already here open. So if we open this product, you can see the name at the end contains the suffix of the tool we have used. And now if we expand the product, we can see that in the bands folder we have reflectance instead of radiance. Remember before it was radiance here, so now we have reflectance. And the important part also here is the mask folder. So here we have all the output of this tool. We have the cloud mask, snow, ice, land, etc. Well, you can see the information in the Snap help. So let's have a look actually to this cloud mask. And for that, we double click in IDPix Cloud. And I'm also going to combine both views. And for that, I go to Windows, Tile Horizontally. Okay, so let's have a look to this mask. Something I didn't mention is that the mask that is produced by the IDPix processor is a binary mask. So it's either true or false for clouds. So white is true and black is false. So let's go to our study area to see how well it worked. So just zoom in, and there we go. So I would say it works pretty good. We have here Cyprus, we have this area here, that is this white area here. All those clouds are selected. Even the clouds here in the middle of the island are identified as cloudy pixels, and all over here. Well, you can see it works pretty well. That's why this is a step in our methodology. We want to derive the NDVI index, the normalized difference vegetation index for this image. So I'm going to close this, and I will show you how to do it. There are several ways to do it in Snap, but I'm using the band math option. So we right-click on the product and we select band math. So we are going to define the expression that will calculate NDVI, and we will create a new band containing the NDVI values. So I'm calling this band NDVI, and I'm making sure that I'm not selecting virtual, because I want to save this band as a real file, not as a virtual band that will be stored in the memory of the software. And once this is specified, we can define our expression. So we go here and we specify the expression, which is this one here. So what we are saying with this expression, it's actually very easy. We are saying if the pixel is classified as a cloudy, so if the IDPix is true, or if the pixel is not in the area classified as land, then we will put to this pixel the value 0. And if not, we will derive NDVI. So NDVI in Sentinel-3 is, as always, derived using the near-infrared and the red bands. So this is the expression. So remember, we are deriving NDVI for those cloud-free pixels, and those pixels are, of course, over land, not over water. It doesn't make sense to derive NDVI over the ocean. So this is our expression, and once we have it, and we see here this confirmation that there is no syntax errors in the expression, we can click OK. And then OK again. So now the NDVI is derived for the complete image, and we can have a look. So let me show it to you. So There we go. That's the NDVI. Of course, it doesn't look very familiar to us because of the colors, so let's change the color. We go here to the color manipulation tab again, and we select basic. And now we can change the color ramp. So I'm selecting the maize vegetation index, and here we see something that is a little bit more familiar for vegetation indices. So if we zoom in to our area, Cyprus, we see actually that we do not have the complete island with NDVI values. This has to load. Okay, so we do not have all the area with NDVI values because this area, remember, was classified as cloudy. So that makes totally sense. We can even change, for example, the color of those pixels that were assigned as 0 by going to the table and selecting here a different color. I'm putting blue because it's water. So for example, this color here, and there we go. So in that way, we can improve a little bit the visualization of the product. So once we have the complete NDVI derived for the Sentinel-3 image, the next thing we need to do is a subset. As you can see, we are still working with the complete extent of the image, and it's very large. And because we just want to focus on Cyprus, it's convenient to do a subset. For that, we go to Raster. Sorry, we select the image and we go to Raster subset. And once we are here, we can define the new extent in different ways. We can use geo-coordinates, so lat-long coordinates. We can also use pixel coordinates, or even we can draw the new extent in this thumbnail here. So if we move the mouse, we can define this rectangle and we can move it over the study area. So I'm using this option today just to show it to you. Once we have this, we can just press OK, and the new product will appear here in the Product Explorer. So you see now we have subset as a keyword to this product. So let's open the result, which is the NDVI, the new subset of the NDVI. So we see now that the extent of this image, of course, it's smaller. That's what we wanted. Okay, so now we are ready to do the last step of this part of the methodology, which is to reproject. So remember, the Sentinel-3 images are ortho-geolocated. So we have latitude and longitude coordinates. But since we have a small subset, it's more convenient, in this case, it's more convenient to change the coordinate reference system to map projection. And more in detail, I'm using today the UTM, which is actually the same projection that is used in Sentinel-2. So to have similar things. How to do that in Snap is very easy. We just go to Raster, Geometric, Reprojection. And again, we have the same interface. So we make sure we are selecting the appropriate input, which is the number 3 with this index here. And we make sure we are saving the product in the appropriate path. Then for the settings of this tool, we can define the new coordinate reference system in 3 different ways, you can see here. But today I'm using a very convenient one, which is the custom coordinate reference system, and for the projection, I'm selecting the option, if you go down, UTM automatic. So this is actually very convenient because the software will locate the product in the correct UTM zone, and it will adjust the parameters to do the reprojection. So once we have done this, we can just press run and the process will start. Again, I'm not running the process to save some time, and I will show you directly the result of this tool. So let me open the output that I have already processed before. There it goes. So here we have the final product after the reprojection. So you can see we have subset as keyword, and if we go up to the end of the product, we have ID picks and reprojected. So, in that way we can keep track of our steps. Now, if we open the same file, NDVI, we can see how it has changed due to the reprojection. So we see now it has moved a little bit to match the UTM zone, which I think is 36 north, if I'm not wrong. So once we have that, we are done with the analysis for one of the images. But of course, we are working with 22, so we have to repeat this step. And it doesn't make sense to do it step by step, as I've shown you, because this is extremely time consuming. But fortunately, Snap has some features that can help us. So, and this is called batch processing. So to do batch processing, the first thing we need to do is to define a graph that contains all the steps we want to do. So for that, we go to create that graph, we go to Tools, Graph Builder, and here we have this window. So we have a read and a write, so let's say input, output, and in between we need to put all the tools that we want to use to process the data. To add that tool, it's very easy. We just right-click on the white space and we navigate to the appropriate path where we have the tools. So I have the graph already created for you. Let me show you. So this is the graph. It's actually the same that I've done before. So we start with a read, the input, then we apply the IDPICs, we derive NDVI, we do a subset, we reproject, and we write the output. So this is the graph containing all the steps. Now, once we have this graph, we can do batch processing. So if you create a graph, don't forget to save it. And once it's saved, do not change any of the parameters here in those tabs, because we will do that later. So now we close the graph and we can open the batch processing option. If we go to Tools, Batch Processing. So the first thing you have to do is to specify which are the images you want to process. So you can use this icon here to navigate to the path of your Sentinel-3 images. For example, I have here the images for May, and I can one by one add the images I want to batch process. So for example, let me just add one so that you see it, or well, let's do two, for example. Okay. So once you have two products, what you can do also is to update the metadata. If you do so, you will see here different information such as the acquisition time, the type of product, etc. So that's actually very convenient. Next, you need to unclick the option Keep Source Product Name. And this is very relevant because when you are batch processing, if you do not unselect this, every output will have the same name. And if that happens, you will be overwriting your products. So we change this, and now we are ready to load the graph we have created before. So we go to Load Graph, we navigate to the path where we have saved the graph, and we click OK. And now we see, again, the same tabs that I showed you before in the graph. So the only thing you need to do now is to go through each of the tabs and put the same parameters as the ones I've specified before when I was doing the procedure step by step. And once this is done, you just need to click Run and the process will start. So of course, I'm not processing all the 22 images right now because this will take some time. So I'm going to show you directly what's the output. And I will show you the output for the month of May. So remember, we are, well, I'm going to close all those products because we don't need them anymore. And let me open the output of this batch processing for the month of May. There we go. So here we have the output of this batch processing step for every of the input images for the month of May. So we can see here the date and NDVI, just the name I've put to, so that we can remember what we have done. So if we now expand, for example, this product and we access the bands folder, we can see here the NDVI. So this is the NDVI for this image. Again, the color, we can change it, and oh, sorry, here. Yes. So we can change the color, we can open all the NDVI images, etc. Well, you can do, well, let me just open another one so that you see that they are different. So this is actually the NDVI for the 10th of May, and this is the one for the 13th. And when you have different images displaying at the same time, you want to make sure that you are using the same color stretch so that you can compare visually the images. And for that, you select, for example, this image as reference, and we click on this option here, Apply to all 2 other bands. If we do so, and we select all, now we are, and then we select No here. Now we are making sure that both images have the same color stretch, and we can check that on the histogram, so that visually they are comparable. So once we are in this, sorry, once we are in this step, the next thing we need to do is to collocate our products. So as you can see, I have 7 different products, each one containing the NDVI of each image. What I want to do is to create a product containing all the NDVI files together. And you will see why this is required. It's required for the last step of our methodology. So this task is done using the Colocate tool of Snap. And in this tool, we define a master and a slave product. Collocating 2 products implies that the pixel values of one product, the slave, are resampled into the geographical raster of the other, the master. And unfortunately, this is a process that has to be done 2 by 2. So you can't collocate 7 images at the same time. So let me show you just the tool, and so that you know how to do it. We go to raster geometric collocation. And here we can define the master and the slave product. So, for example, in this case, the slave product, which is the NDVI image of the 10th of May, will be resampled into the raster grid of the master product, and they will be combined. So, as I told you, this is a process that you have to do 2 by 2. So you have to combine this, and then the output of this operation has to be collocated with the 3rd product, and so on and so on. So I've done this process already, and I will show you the output directly. So for that, I'm going to open the product. So here we have Colocate May. So if we expand this product now, and we go to the bands folder, we can see now that we have here NDVI 1, which is the NDVI from the first image. We also have NDVI 2, and we go down NDVI 3. So as you can see, we have all the NDVI products in the same, the NDVI files in the same product. But as you can see, we have many, many other bands that are together. So actually, this is not very convenient because it takes a lot of time to locate the different files. So the next step is to do a band subset, to remove all those bands that we are not interested on. And for that, we go to raster subset, but now instead of doing spatial subset, we are doing band subset. So here we have all the bands of the collocated product. We can just remove, select none, and then one by one we select NDVI 1 and keep going, NDVI 2, and so on and so on. If you go down, you will find NDVI 3, 4, 5, till 7. So I've done this already. Let me just open the product. So if we do the subset, this is what you get. The same name with the keyword subset. And now if you go to the bands folder, we can see that we have NDVI 1, NDVI 2, 3, and we do not have all those bands that were there before. We do have those collocation flags, which refers to the quality of the collocation process we have done before. But okay, the important thing is that we have much less bands, and it's easier to find them. So now we are almost done with the analysis. The next thing we want to do is to derive a mean NDVI value for each of the pixels of the image. And how to do that? It's again very easy. We are using the, again, band math option, which is actually a very powerful tool. So we right click on the product and we select band math. And now we are going to specify a new name for this new file that we are going to create. And it will be called mean NDVI. Again, we unselect the virtual option to save the product, and we are ready to define our expression. So we click on edit expression and we specify the mean calculation. So this is actually basic math. We say NDVI 1 plus NDVI 2, 3, 4 till 7 divided by 7, just a regular average. And we say OK. And once this is done, we have our output, which is located in the bands folder. You can see it here. Now we have mean NDVI. So let me change the colors again using the same procedure as I did before. And I'm going to put the blue color for the no data, which is 0 in this case. 2. Yes, simple. Okay. So this is the mean NDVI pixel values for the month of May. So let me just close all those products that I don't need anymore. And now I'm going to show you the same product that has been processed already for the months of June and July. Remember, we are processing 3 consecutive months, May, June, and July. So I'm going to show you the equivalent product for June and July. So let me just open it very quickly. This is June and this is July. So again, let's open the NDVIs, the mean NDVIs of those months. So here we have June, and let's open now July. So again, make sure once, if you are comparing visually different images, make sure you are using the same stretch of the course. For that, we select, for example, this image as reference, and we say, okay, select all, and okay. And now here we say no to make sure we are using the same stretch. Okay, there we go. So we can combine all the views in Windows tile horizontally, and let me just move this a little bit. And now if we move around, we can see the evolution of the mean NDVI value over the month of May in this area here, the month of June, and the month of July. So this is one way to perform this land monitoring, let's say in a visual way. But there is a great capability in Snap which allow us to analyze time series. For that, we need to open the time series tool of Snap, which is located in this icon here in the main toolbar. So if we click here, and now let me just close those views, we don't need them anymore. I'm just leaving this one for reference, and I'm doing this a little bit bigger. Okay, so we have this time series tool, and now we are going to create a graph that will show us the evolution of this parameter, the mean NDVI, over the 3 images we have. So for that, we first select the images we want to include in this analysis. So sorry, I didn't show it. We click here in this icon, and we select, okay, I forgot to tell you something. When you when you do some type of band math, make sure you save the product so that everything is stored and everything works properly. So just right click, save product. Okay, so I was saying, we go to the time series analysis tool and we open the settings, and we specify that we want to include in this analysis the 3 images we have here open in Snap. So we select the icon add open and we refresh. So as you can see, we have all the metadata. We can also change the color of the line of the graph that will appear, for example, to red. We can also change the name, because now the graph is called graph 1, so that doesn't make sense. So we can just change it to something you like. So for example, NDVI evolution. And we say apply. So now we can just close this, and now make sure you specify which is the common band that you have in the 3 products that you want to use to compare the values. So we want to compare the pixel values in the mean NDVI band, and we say okay. And now if we move around if we move our cursor over the image, we can see the evolution of the mean NDVI values in our time series. So you can see in the X direction, we have the time, so from the 1st of May till the 15th of July. Of course, our images are those points here. They're not very visible, but okay. And here we have the values in the Y of NDVI from 0 to 0.75 in this case. So if we move around, we can just see how this changes. So let me just zoom a little bit. For example, here it's kind of stable. In other areas it increases, etc. Well, that's up to you how you want to create. And the good thing is that once, for example, you are doing a specific analysis and you want to export this graph, actually you can. So by using those buttons here, you can export the file as a CSV to be opened, for example, in Excel, or you can also export the graph as an image to be used, for example, in a report or a project, etc. So you can exported as PNG, etc. So, that's all for the exercise. I just want to now highlight a couple of take-home messages that I think are important based on what we have learned today. So let me go back to my presentation. Okay, so if we take into account all the things I have explained today, with the new Sentinel satellites, the challenge in satellite remote sensing is no longer data availability, but rather how to store and process all the information. In addition to all that, it is necessary to explain how the data can be used and support users in their applications. The RUS service is here to solve those problems by providing virtual machines to store and process the data, and by offering a dedicated help desk supported by a team of remote sensing experts to help you in your projects with Sentinel data. So that is all for this webinar. Before moving to the Q&A session, let me tell you again how you can repeat this exercise by your own. If you want to practice the same analysis I've done, or if you want to adapt it to your study area, etc. So the thing you have to do is to go to the rus-copernicus.eu website, register as a RUS use service, and then request a new user support service. And during your application, you have to specify, as I showed you before, the training code. So the training code for this webinar is LAND04. So when you're doing the application, put LAND04, and in that way, we know the type of virtual machine you need, and we will give you all the data I have used today so that you can replicate the same analysis, and you will also receive a step-by-step guide containing all the information I have explained. So that is all from my side. You can see here training code, our websites, the contact information, and of course we are in social media, Twitter, LinkedIn, Facebook, and YouTube. So please follow us. We post all the news about RUS there. If you want to stay updated with webinars, face-to-face events, and everything we do, you can just follow us and you will receive all the news. Okay, so as I said, thank you very much for joining this webinar. It has been a pleasure for me to guide you through this topic. I hope you have learned something today. If you wish to repeat the exercise, please feel free to register for RUS. It's free. And I'll see you in the next one. Ciao.